Okay, now let's consider the yellow expression that I repeat is the reversal and the wall expression of whatever occurs in the optical communication. Okay, so you have to memorize this expression. Okay, for the exercise of the second part. Okay, just I try to underline this. Okay. Let's simplify this expression by dividing by the term E squared, that is a constant, and the G average. What we obtain, alpha P squared, will I divide, okay? Then, what occurs below? Below is occur that I have average squared divided G squared that gives a variance. That is called this 1 plus variance factor form. Figure of merit of the APD, this one. Then here I have this that disappear. Okay. And here I have N or C divided G squared, because you see that these are no multiplication because these are the term electrical. So what we observe that even this is divided by G squared. So what we observe that as expected. Okay, the APD here, we are considering now this first expression, detection, that is direct detection. Okay? We consider a direct detection, so the number 1, okay, and we consider an APD. If APD exists, okay, this is an increase of the current here. So in other terms, here I have my signal that arrives B signal. I hit the APD, but if APD exists, if this is an APD and not a PIN, okay, this looks like a small amplifier that amplifies, that is an amplification, okay, of the current flowing in my resistor, okay, before to be amplified. This is an electrical amplifier, okay. So here I have a voltage that increase. This is voltage because it's a current over RL, this is voltage. So this voltage increase because this G gain. So this means that this remains the same, but this is a primary current. This primary current that increase is seen by the noise as equivalent to the increase of the signal. And so it's why this increase of primary current don't move the optical noise. You see that the optical noise is not affected, okay, but decrease the electrical noise. You understood? I have to repeat. So it's a sort of electrical amplification. It's not electrical amplification, because electrical amplification occurs here, increase the noise, the Johnson noise, because any time you amplify through electrical amplifier, you introduce noise in the system. It's a thermodynamic theorem. You cannot avoid this. But this is look like that this power increase is not true, but is similar. Okay? Now, let's now take the hypothesis that we have no amplifier inline. That is the case 1. If there are no amplifiers here, that is, we have just the transmitter and the receiver without amplification, and we care about the optical fiber that no the sun arrive inside, so I shield this in a box, or avoid that some light from the ceiling arrive. Okay, so I seal the transmitter, If I seal the transmitter, all the noise component disappear. The optical noise component disappear. You agree? Because I consider my single mode transmission. I have no sun, no moon, no light. I have no amplifier, so there are no source of thermal radiation. You understand? No? Why not?
I understood that we need to isolate the system from any other source of light.
Yes.
Yes.
It is not difficult to do because I have a transmitter in a small box, like this box.
Yeah.
No? Here the LED I close with a black wall. I avoid that some light enter.
To mitigate the effect of interference, yeah.
No interference, just I avoid the light enter. And so I have only laser here. So coherent light with modulator. And then I launch in the fiber. In the fiber, no light enter. Now you know because it's impossible to enter in the core of the optical fiber. Because to have to match the beta. So it's very difficult. So you cannot enter in the fiber. Then you arrive at the receiver, and when you arrive at the receiver, there are no optical noise.
Yes.
From thermal origin. No, there are optical noise from quantum origin, from the laser, but not from the thermal origin. So, if I consider this, I may remove, since the NO is power of the optical noise divided by O. So this is energy of the optical noise. The optical noise energy is 0, all this is 0. Because this bracket exists, but not this. Not this term NO. Okay? So the term NO cancel this bracket. Okay? So what remain? Remain the power of the signal, the power of the noise. But this is true, because you may have a power of residual noise. Okay? And the electrical term. Okay? Then, these are shot noise term, these are Johnson term, and this is dark current term. What I do, I divide the numerator, you see here is alpha PS squared, because I remind you that is signal square divide variance, the denominator are variance, otherwise it's not possible to sum, okay? I may do the same with the square root of the standard deviation, but of course I prefer to use variance, okay? So, alpha PS. Now divide the numerator by alpha PS, and I divide here also the numerator by alpha PS. So what we obtain this expression. Alpha PS in the numerator, because I divide by alpha PS. And 1 plus Pn divide Ps, NOC divide alpha Ps, is this one. So it's very strange now, because what we obtain that the numerator is depressed by this denominator. But if you increase the power that arrives to the signal, to the front end, you decrease all the denominator term. Magic. You see? You agree? Just algebraic manipulation, no magic. That it look like magic. Okay? Not a trick, but it's algebra. Okay? Then, this is very important consideration. the availability of the powerful signal make negligible the noise term and lead the SNR to short noise limit. That is, this electrical term, the noise coming in this current from KT goes zero if I have power. So just it remains this term here. This term we know is the quantum origin term or particular term or short noise term. And this goes zero. Okay? And then we have two situations. You suppose to have Pn in the order of magnitude of Ps, this remains, or Pn much more lower than Ps. This is the remaining signal to noise ratio. So very simple expression. Okay, because I have enough power to beat the noise, electrical noise term. This expression that is derived by the general expression as a particular case, okay, is called short noise limited. You may find many times in the book or in the theory or in the catalog of the optical communication, this expression. People say, I am working short noise limit. So what means when he says I am working short noise limit? Means this expression. Alpha Ps divided 2Bm, you see that you are inverse proportional to Bm. F, if you have an APD, otherwise this is 1, okay, 1 plus Pn divided Ps. So the power of the noise divided Pn. Now we have two situations. You suppose that Pn is larger than Ps, or you suppose Pn is lower than Ps. Okay? You follow it here? Go ahead. Uno, Pn is equal to Pn large. Under this condition, the previous expression became this one. Okay, because this one, this is much more larger than 1, so you suppose Pn divided Ps is 3, so this is 3. So I remove this one, and this go to numerator, so Ps go to the numerator, okay? Because I remove one, okay? Then in first approximation we obtain this one. Okay, this is called background noise limited. Why background? Okay? This is recovering the optical communication system but without fiber. So you suppose to have an optical communication system without the fiber. So I transmit this. I am here the optical filter. I am here on the hill of a building, maybe, okay, and I receive. In this case, I am not able to remove the sun noise. Or in the light, if I am an astronomer and I look for the star, I am not able to remove from the moonlight, okay? Even the astronomer use optical communication system because the telescope is nothing more than optical communication system. Because the telescope sees the light of the star. Okay, so this is the condition. So unwanted thermal source can be very high or no. And in this case, this is the maximum obtained background noise signal. 2. Now suppose that Pn is less of Ps. Under this condition, the expression simplifies more, because you just have alpha Ps divided F2Bm. Or if the photodetection without gain is used, alpha Ps divided 2Bm. So we already met this expression. You remind was the first expression that I propose you in considering the signal to noise ratio. This expression is called quantum limited, quantum noise limited, okay? because you cannot compress more this signal to noise ratio. This is a limited, because in this case you suppose to have in fiber, so with a complete shield of any thermal light. We have no optical amplifier that insert optical noise, so we have nothing. And you have enough power to beat and to cancel the drawback caused by the electrical signal. In this case, you obtain alpha PS divided 2Bm. I underline that this expression, now we see how we obtain this. Is obtained because it's been depressed because the high power that arrive in the signal depress both electrical and optical noise. So I remind you that this is obtained because this is the sum of this expression. So if I have a very low signal, very low PS, I am not able to cancel this term. And then I cannot go short noise limited, and then I cannot go quantum noise limited. Okay? You may ask why you cancel here NO in the previous expression. Somebody may ask why you cancel NO and you don't cancel PN. Because NO is by definition PN divided BO. So if BO is 100G, okay, could occur that PN, which is NO by BO, okay, even if NO is very small, to suppose 10 to minus 9, BO is 100G, so this NO time 10 to 11. So the bandwidth of optical filter is so high that even a very small presence of noise gives power. But this is energy. So energy is cancelled. Okay, so this is why in the expression Pn remain why NO is cancelled, okay? Because NO is the joule, is the energy, while Pn is a power, okay? Okay, let's look more in detail SNR quantum limited. This is very important, SNR quantum limited, already said this, because it's given for the designer, for the engineer that project the system, the maximum available SNR. It's not impossible to reach. It's quite easy to reach in optical communication this, because if I remove the electrical term, if I have enough power, I may reach this quantum noise limit, okay? Let's see more in detail some meaning of this expression, okay? Alpha PS divided 2Bm. Instead of alpha, okay, I put the explicit expression. So it means that this became now alpha PS divided 2Bm, now became eta Hν PS, okay? It is this one. If you read this expression in this mode, you may suppose that in the numerator you have the power of the signal, and in the denominator you have the power of the voice state. Because this one, Hν divided 2, okay, is the void state. So this residual that comes from the general expression of the signal to noise ratio, in effect, could be written now as the ratio between the two powers. Okay? Okay? The void state energy cannot be extracted, okay? But enter in the photodetection system as a variability that even the more ordered light present, we already seen this in the photodetection process, because if you enter with a laser light, that is with a more ordered light in the system, okay, you have a Poisson variance. In effect, this is a Poisson variance, okay, because this could be interpreted, the expected value of n could be interpreted as the average squared divide variance, that is exactly the Poisson variance. Okay, we already said about Glauber. Also, you may give another interpretation of quantum limit SNR, because you may interpret this as a power of the signal divided power of the shot noise, okay? So power of the void state or power of the shot noise play the same role. The first expression refers to the process in the optical domain, when you consider just the optical domain, okay? While the second expression underline the presence of the photodetection process, but you obtain exactly the same expression. Okay, so this is another vision of the signal to noise ratio quantum limit. Okay, so you may have an optical domain vision or electrical domain vision. Okay, these two visions concur. Okay. Then we look more in detail the importance of the depression of the electrical term. We see that in direct detection, if I have enough power, we may reach quantum limited expression. For the communication engineer, the communication engineers are very interested to reach the maximum signal to noise ratio, that is to remove the electrical originating noise, because the presence of this noise causes an unnecessary drawback or penalty. In other terms, if you are a communication engineer, you pay for obtaining the maximum signal to noise. And the maximum is quantum limit, because quantum limit cannot be overpassed. So any introduction of further denominator here give a drawback or penalty in the signal to noise ratio. So you are forced to do your best technology in order to avoid this. Okay. Let's observe more in detail what we have to do. We have to increase the alpha PS, G squared, in order to beat the Johnson noise term that I remind you is 2T divided A squared RL. So I have to verify this equation, no? Because if I verify this equation, the electrical term disappears, because usually the dark current term is lower than this. So if this is verified, I may remove all the electrical terms. But the satisfaction of this inequality present a deep impact on the optical communication system design. Why? Let's analyze the single term here. You see that this is the power of the signal. This is the input impedance, and these are the temperature or working temperature. Okay, the other are constant. power. Let's analyze the single term, power of the signal. What is the power? Power of the signal, okay, is the power not of the transmitter, but the power that arrives here in the receiver after maybe 100 or 200 kilometers of propagation. So this power of the signal suffers for the attenuation in the optical fiber. You remind attenuation alpha. So this number is usually very modest, very small, because you have maybe 20 or 30 dB of attenuation after a long journey of propagation. So this term is very small. Since this term is very small, it's difficult to verify this inequality. Because this means that this term left should be much more smaller than this term. And this poses some problem. Why? Another problem is this one. The bandwidth of your receiver, the bandwidth, go like 1 over RC. You agree? The bandwidth go like this. But since C is a constant, this means that the 3 dB bandwidth of your receiver is inverse proportional to RL. So this means that for high bit rate, RL should be very high. So this gives a problem, okay? So you cannot compress, in other terms, much more this value of RL. G squared. This term gives you an idea of the gain of the APD. But if you increase much this gain of the APD, you increase the variance introduced by the multiplication factor. So you increase the figure of merit of your APD, and this gives a drawback. Okay. Also, if you increase again, you have some problem in cost and packaging of your APD. So, in summary, you have to verify this inequality. Okay. You see that left you have here the bandwidth. Instead of R, I put a bandwidth. And right, you have here the attenuation coefficient and the gain. Okay, in order to verify this inequality, we need a compromise between the different needs of the link design, because if I take a long link, this term became smaller then, so you are not able to verify this inequality. If I take a very huge bandwidth, this term became large, so it's difficult to verify this inequality. Okay. If I am without APD, this G squared disappears. So this means that it's very difficult to verify this inequality, and so on and so on. So when you have to organize the design, the project of your link, you have to verify this inequality. You may also neglige this inequality, but in this case you have to consider the electrical noise that arrive in your system, so you are not able to reach the quantum noise limit. So you have a penalty due to the electrical noise. So this is why it's so complex, the design of the simple link in direct detection, because you have to verify this inequality, okay? I repeat. So there are some mixing between theoretical and practical consideration, because this equality comes from a theoretical consideration, but this is very practical, because you have a power, attenuation of the fiber, bandwidth of the signal, and it means that if you deal with large bandwidth, you have to pay a tribute to the link. In other terms, for short link, this term is very small. You suppose a 10 kilometer link, so this term is very small because you have a 2 dB. No? So for short link you may have a very large F, that is bandwidth, okay, because you have no problem in propagation, in attenuation. Also you may avoid to use a large APD, because it's enough a small, again, APD. Because if you put 10 here squared, it's 100. So now let's put some number, okay? Because if you put a number, it's better to understand, okay? Let's see a numerical example. Let's consider a link without APD and 100 kilometer long, okay? In this case, the transmitter average power be 10 milliwatt, okay? Hence, the receiver average power will be 0.1 milliwatt because I lost 20 dB. With 0.1 milliwatt, we originate a count rate of the order of LPPS, that is 0.8 10 to minus 4, okay, divide the energy of the photon, 128 10 to minus 19, okay, that give you approximately to 6.3 10 to 14 count second. This is my count rate. PS is 10 to minus 4, it's 0.1 milliwatt in this case, but it's very high power, usually it's even more lower, okay, and the 0.8 is eta. So this is my count rate, that is 10 to 14. So the count rate squared is 40 10 to 20. Okay. Now, I have to organize the link in order to avoid that the variance overpass this number, okay? Let's go to the variance. The variance of the Johnson noise, okay, is 2K squared divided RL. So 6.3 10 to 15 count second, because Kt is 25 milliev, you remind. So 0.025, 1.6 10 to minus 19. 2 is 2. E squared is 1.6 10 to minus 19 squared. RL, I suppose 50 ohm. Okay, typical input impedance. Okay, so 50. So I have a 6.3 10 to 15. From what I have that the variance of the Johnson noise is 40 10 to 30. So if we compare 40 10 to 30 with the previous number, you see 40 10 to 28, this means that my signal present a count rate like this one, and the variance of the signal that arrives is 2 orders of magnitude larger. So you have the Johnson noise that completely overpass the signal noise. So this is not acceptable. Then, in order to the count rate, submerge the count rate of the signal, under this condition the receiver is being impaired. So this means that in order to restore an acceptable operation, we have to use an APD. As example, if we use an APD with a gain of 100, okay, the count rate became 6.3 10 to 18. Okay, because I just multiply this, okay, by the count rate, okay. So this means that in this case, okay, even if this value is decreased by the factor f, is enough to combat the Johnson noise. Alternatively, if I cannot use an APD, we need to reduce the length of the connection, or I need to reduce the bit rate, because if I reduce the bit rate, okay, in this case, okay, I verify again this inequivalence. Okay. Once removed this electrical variance, you cannot increase the signal to noise ratio, because at the best the signal to noise ratio became the quantum limited with 0.1 milliwatt in power here. Okay. So this is the meaning of this sentence. It is, in order to verify this, I have to consider that I cannot move as replace PS and RL and G average. Okay, so we may interplay with these three terms in order to verify this inequality. And this is the duty of the optical engineer. Okay, so you have to balance your region. Okay, we stop here.